Hello everybody, today we will be going over the inverse of a matrix. This will be part of week 5 of Carnegie Mellon University's 21-41, and you will want to look at the next video to understand the properties of matrix inverses. So let's first revisit the equation ax equals to b in linear terms. So intuitively, if we wanted to acquire x with real numbers, we would say, well, x equals to b over a, provided that a does not equal to 0. And sequentially speaking, if we break this down into pieces, we would simply multiply both sides by 1 over a, which would equal to 1 times a times x equals to b times 1 over a. Now this will be an important concept because later we will see that a times the inverse of a will equal the identity matrix. So of course now we're going to ask ourselves, well, how do we do this in matrix algebra? Well, we denote the inverse of a matrix as a prime. And in order for a inverse to hold, a prime times a must equal to I, and a times a prime must equal to prime. Now, because we can do this both ways, this means that a must be a square matrix. So following this line, we can also see that given the equation above, x will equal to a prime b, which is later you will see similar to x times 1 over ab. Alright, anyways, so let's start with a definition of an inverse. So given a matrix A, which is by n dimensions, the inverse of an a prime, is an n by n matrix such that a prime a equals to I, which equals to a prime. Now, note that I equals to in, which is the n by n identity matrix given n. Of course, if a prime exists. So now let's look at an example. This is example 3.22 in the textbook if you're following along. So consider the matrix A, which is 2, 5, 1, and 3. And we're going to try to find a prime, which we will denote the elements as a, b, c, and d. So what are we trying to do here? Well, first of all, we know that a times a prime must equal to the identity matrix of 2, which will be 1, 0, 0, 1. So, simply we just do some matrix algebra. We know how to do multiplication, row times column, row times column. And then it will be pretty easy for us to get some equations such as 2a plus 5c equals to 1, b plus 3d equals to 1, 2b plus 5d equals to 0, and a plus 3c equals to 0. If you don't know how I got this, please stop the video and then try to do this yourself. Now, after doing some algebra, you'll see that c equals to -1, a equals to 3, d equals to 2, and b equals to -5. Then a prime, if we plug the numbers in, we get 3, -5, -1, and 2. Now, just by doing some multiplication, it is pretty easy for us to see that multiplying these two together, both ways, will give us the identity matrix. Right, so now let's consider another example. This would be example 3.23 in the textbook. And we want to show that the zero matrix is not invertible and that b equals to 1, 2, 2, 4 is also not invertible. Now, let's consider the reason why the zero matrix is not invertible. Well, we know that anything multiplied by the zero matrix would be 0. So in order for us to make the zero matrix invertible, there must be a 0 prime such that 0 prime times 0 equals to the identity matrix, which is simply not possible because, as we mentioned already, anything multiplied by the 0 matrix is going to be a 0 matrix. Now let's consider why B is not invertible. Well, once again, we can separate B into a equation. Well, we can see that A plus 2C equals to 1 and 2A plus 4C equals to 0. Well, this basically tells us that 2 equals to 0, which, well, is a logical contradiction in math. So let's talk about some remarks we have. So even though matrix multiplication isn't commutative, if A prime exists, A prime A and AA prime must equal to each other. And this leads us to 3 theorems. So theorem 3.6 states that if an inverse exists, it is unique. So what this means is that there's only one inverse per every matrix, which will be important for our later examples. And then also theorem 3.7. So if A is an invertible matrix, then the system of equations AX equals to B has a unique solution such that X equals to A prime B for all B in Rn. So what this is basically saying is that if A is invertible, it must have a unique solution for X. Now the proof is very long, so I'm not going to go over this in this video, but if you feel like proving it, which I suggest you do because it is very important for this class, you should probably do it. So now there's another theorem, theorem 3.8. If A equals to ABCD and A is invertible, then A is invertible if AD minus BC does not equal to 0. This is what AD minus BC is what we will call the determinant, which you will see later in this video. So given the determinant, we will see that A prime equals to 1 over AD minus BC multiplied by the matrix D, negative B, negative C, and A. Now, we're basically simply swapping A and D, and then we're just multiplying negative 1 to negative B and C. Yeah, so AD minus BC is called the determinant, as I mentioned previously, and then we denote it as DETA, and it basically determines if a matrix is invertible in our context here. So what theorem 3.8 is basically saying is that A prime equals to 1 over determinant A times D negative B negative C A. Now, of course, there's another proof associated with this, but I simply do not feel like going over it, but I encourage you to prove it yourself. So now let's look at another example. This is example 3.24. So let's find the inverse of A equals to 1, 2, 3, 4, and B, 12 minus 15, 4, and negative 5. So of course we're going to try to find the determinant first. So the determinant of A would be 4 minus 6, which is negative 2, which does not equal to 0. Hence A is invertible. And the determinant of B is negative 60 plus 60, which equals to 0, which tells us that B is not invertible. So as you can see, the determinant is very useful in this context. So to find A prime, we simply plug into the formula, and we will get negative 1/2 over 4, times the matrix 4, negative 2, negative 3, and 1. And this will give us negative 2, 1, 3 over 2, negative 1/2. Yeah. And now let's consider a different type of example where we're trying to find the inverse we were trying to find the solution to a linear system using the inverse of the coefficients matrix. So given the system of equation x plus 2y equals to 3 and 3x plus 4y equals to negative 2, well, we can write this into a matrix in the matrix form where it's 1, 2, 3, 4 times xy equals to 3, negative 2. So as you can see, we can clearly label these as A, X, and B. Well, actually, let me erase B. Yeah. So how do we find this? Well, we first find the determinant, which equals to negative 2. Well, this will be the exact same matrix we found in the previous example. So it would be pretty easy for us to find the inverse. And then we simply times it by B, which will give us negative 8 and 11 over 2. So my final remark for this video would be, intuitively it might seem pretty easy for us to use x equals to a prime b, but it is only useful to solve 2 times 2 matrices because any matrix that is above a 2 by 2 is better solved using Gauss-Jordan elimination. Well, I will link my notes to the description, and thank you so much for watching. Happy studying!